So, okay, so what I'm going to do today is to present a sort of overview of magnetospheres. I'll talk a little bit about comparing planetary magnetospheres of different objects. And in fact, in many ways, we can think of these as all magnetospheres. But I'm going to emphasize particularly different planets. Okay, but before we do that, I actually have a question for you, which is I'm curious to know, were you asked this on Friday and I wasn't here? What are your interests? Can you just wave your hand in the air if you're basically see yourself as a solar physics person, astro, you know, okay. How about if you work on heliosphere, solar wind, that sort of thing, okay. How about Earth ionosphere, magnetospheres? Okay. How about planetary objects? Fewer people, right, but there's some. And not sure, yeah. A few of you, good, okay, good. That's just useful to know. And indeed, we did plan to have a mixture, but it's good for me to see that. Okay, so like I said, we're talking about planetary magnetospheres, and we're talking about objects from the small environment of Mercury that could fit, all of the magnetosphere of Mercury could fit inside the Earth. And then you take the Earth's magnetosphere, a very dynamic environment in which we live, all of that would fit inside the planet Jupiter. And then we take Jupiter's vast magnetosphere, the largest object in the heliosphere, except for the heliosphere. When we put that into the sphere of influence of the Sun, it's pretty small compared with the heliosphere. And this is a little out of date, and the boundaries are a little different. And of course, Voyager is now somewhere in here. Okay, so let's look at these magnetospheres, and Sabina talked a little bit about these different magnetic fields. Earth, Saturn, Jupiter, Uranus, and Neptune. And here we've sort of, I put in an offset tilted dipole. This is a poor approximation, as we'll cover in a minute, but it gives you a sense of these magnetospheres with Earth and Jupiter tilted about 10 degrees, Saturn with its rotation and magnetic field axis very tightly aligned, and then Uranus and Neptune with not only highly tilted magnetic fields, but also offset from their centers quite a bit. Also notice what we use, the word obliquity means tilt of the spin axis. So we think about the orientation of these magnetic fields with respect to the solar wind. We have to think about not only the relationship of the spin axis to the radial direction from the solar wind, the direction that the solar wind comes from the Sun, but we also have to think about the orientation of the magnetic field, which changes not only because of the tilt with respect to the spin axis, but of course the orientation of the spin axis will vary over the seasons. And if we were to talk about Uranus and Neptune, this would be an extreme situation. So Sabina showed this nice diagram of the surface fields of the planets and illustrates quite well the similarities, except for the polarity of Earth and Jupiter. So right now, the orientation of the Earth's dipole is opposite to that of Jupiter and Saturn. But this shows you very nicely the highly aligned magnetic field of Saturn and the offset of Mercury and so on. And the highly non-dipolar magnetic fields of Uranus and Neptune. So let's just mention very quickly this issue that we can take a magnetic field, and if we're interested in the magnetic field of the planet, not the magnetic field of the current systems outside, but if we ignore all of the external current systems, we can describe the magnetic field as a gradient of a potential, and that we can conveniently make an expansion of that potential, and we can take this as a series of functions. These are the Legendre polynomials here, and diagrammatically they look like this. So you have a variation in complexity in latitudinal structure, and then you have a variation in complexity with longitudinal structure, So those are the n equals numbers and the m numbers. And you can then have a series of, you take a bit of each of these coefficients. So you say, I'll have a bit of this and a bit of one of these, a bit of one of the others. So to make up the field that I have, I'll take a bit of that and a bit of that and a bit of the other. And the amount you take of each will be these coefficients, the GNMs and HNMs. Add them all together. But notice, but notice that each of these N's and M's decrease in power with radial distance as you increase N. So if you have a large, more complicated field, that will be tightly confined to the object and will decrease with a high power radial distance. So you go far enough away, everything is a dipole, okay? Now this expansion is used for all sorts of things like the cosmic microwave background. It's used for helioseismology, common one. And for the Earth, just to give you a sense of the extreme, you can look at the Earth's geomagnetic reference field, and these are different years. I don't expect you to read these, but just to give a sense of the immensity of the information we have about the Earth's magnetic field. This goes back to 1900, every 5 years through to 2010. These are all of the G10s, H, blah, 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 N and M's. Goes all the way up to 13 of each, 4 pages later. And you can go and see this. You can download it. There's actually a Fortran program. And latest thing, 2011 field is now out. You can go get it. But it gives you the magnetic field as a function of time and so on, and you get the declination. That's how much you have to offset to get north by a certain amount, and then inclination is the tilt vertically, and then this is the total intensity. And you can see the South Atlantic anomaly here. So you can go get these magnetic fields for the Earth, but you can also think about them for the planets. And so I put up here from one of Sabina's papers, here we have those maps again that she showed, that these multipole coefficients, if you take the ratio to the dipole, you can see the degree of complexity. So if we look at compare them to the dipole, these different planets, you'll see for Earth and Jupiter, they decrease by, this is log scale, right? So orders of magnitude when you go down from the dipole to the next one. And with Saturn, it's 2 orders of magnitude down to the next one. But then what you see is that Uranus and Neptune, their high-order multipoles are almost comparable to the dipole. It's a very non-dipolar field, and a dipole is just a really pathetic approximation in their cases. Okay. So then let's think about planets or objects that don't have a magnetic field, have crustal magnetization left over from an old dynamo. In the case of Mars, the dynamo died about over 3.5 billion years ago, and we don't know whether the moon had a dynamo. What we see when we look at the moon, and to some extent the Earth and Mars, when we go to higher degrees of complexity, so now we're going to n greater than 10 or so, that we see the effects of the crustal magnetic fields, which are very dominant and very strong in the case of Mars, and quite weak in the case of the moon. Okay. So, let's do a little recap. We can talk about magnetospheres. I know that Mark, I think it was Mark, who talked about cavities, current sheets, and flux ropes on, let me see, what day was that? Friday? Can you remember Friday? And he talked about these being the basic 3 ingredients. Now, here's a magnetosphere. Good sketch, say, of the Earth's magnetosphere. I want you to chat with your neighbors and look at this diagram and tell me where would you find each of these in this magnetosphere. So go ahead. Little quiz while I have a sip of coffee. Okay, first the easy one, the cavity. Where are you going to find the cavity? a region that is sort of enclosed environment that doesn't have a lot of stuff in it. Is that a way of calling it a cavity? What were the definitions that you came up with on Friday for a cavity? Self-contained, enclosed environment. So where? Here, do you want to point to, show me a cavity. It's easy, you just hit that.
Yeah.
That red, there, yeah.
So let me see, is in here?
Inside, the closed region though, you sort of need to stick with in around here and in around here, right? So you would say this is the cavity, right, okay. What about current sheet? Somebody want to point to a current sheet? You willing to point to a current sheet? Use that red thing there. No, that red thing, yeah. Right, so how did you pick it out? What were you looking for to say that's a current sheet? There's a change in magnetic field. This is what I do, current sheet, right hand rule, curl, right, curl B. So you can see there's a curl there. Where else is there a curl? You said N2, right? What about the magnetopores? Right, I can't reach the magnetopores, but you see here, you've actually got a curl of B here, right? You've got a curl of B here. It should be a bit more pronounced, but on the magnetopores, there's a curl in the B. Okay, and then finally, flux rope, the obvious one. Where's the flux rope? Yeah, the plasmoid, right? We don't really know from this what the in and out of the board extent is, but we assume that there's some kind of a current sheet. There's a current that runs along it and produces fields that are winding up around. Okay, good. Okay, so let's think about these. We have this magnetic field. It's sitting in the solar wind. Yes? Yes. Do we know that this is actually a flux rope from in situ measurements? Indeed, I think there are observations that show, it's a little difficult with a single spacecraft, but now we have multiple spacecraft, Cluster and Themis, that are flying through, and so you can build up a sense of this thing. Even if it's moving over you, you can sort of sort out space and time and work out that, yeah, there's a rope going. Sometimes it's just more ropey than other times, but yes, we have actual observations of them. Yes, someone over here had a question. Well, a flux rope implies that it's got some twist like this, so that the field structure is not just a field like, a tube without uniform, but the field varies along the tube as well, and you have some twisting, right? Braided as in twisted rather than necessarily the field lines are, tied up in a complete knot. But in fact, they can be. There's a degree of complexity from a simple flux tube with just a uniform field, and the complexity you get when you have more tied up tangles. They can get very tangled. Yeah, good point. In fact, maybe that's a good point, that rope isn't a good word because it implies a level of braiding, which is not always that strong. Yeah, Nick.
So this picture is a wonderful idealization that completely whitewashes over the normal complexities that we'll probably see at least in some of the lab.
Right, and it certainly it ignores the dimension out of the board, which is a major part of these structures. Okay, good point.
We draw everything in 2D, and there has been years of debate on if it's an island or a cluster, and it's a silly debate when you think about it. Obviously, a 3D structure, but when you draw it, it's 2D.
Right.
When you draw something,
Yeah. Right. Yeah. Up here, you mean?
Negative neutral point that will be above the arrow. In the Magnetosphere.
You mean up here? Down in here? Where do you mean? Point. Because I can't see what you're talking about. Because because there's you think there's a curl of B in there. Yeah, yeah. I guess the answer is wherever there's a curl of B, there's a current, right? But whether it's, you know, the shape and the direction of it and the strength of it. Current sheet in the cusp, I have no idea. Anybody tell me whether or not we've seen current sheets in the cusp? Mark is nodding his head yes. Okay. Okay. Let's talk about magnetospheres. We're going to talk about these in general, and my philosophy is going to be to talk. I couldn't do all of the magnetospheres. It's impossible. I'm just going to concentrate on Jupiter and the Earth, or the Earth and Jupiter. Though we'll have some option for discussing some of the other ones later. But they sort of are extreme cases, if you like, of magnetospheres, the two different kinds of magnetospheres that I want to contrast. But think about, if you're more astrophysically inclined, to think about how if we go out and look at exoplanets, and we find exoplanets around different stars, which we found, many of them, but what kind of magnetic fields they might have, what sort of magnetospheres they might have, and how we might look for them. So as we describe these two, Earth and Jupiter, think about what we might do when we go and look at exoplanets. Of course, being exoplanets, they may be completely different. In many other ways, they are completely different from our planets. Maybe their magnetospheres are very different too. Okay, so we have our obstacle, which is the magnetic field. We have a supersonic wind coming in, and it therefore has a shock when it hits this obstacle. The obstacle has what we'll call a standoff distance of Rm. We have a bow shock, and the bow shock for the Earth is roughly 1.3 times this distance between the magnetopause and the planet. And the physics of the shock, David Burgess will be talking about shocks later in the week. But the whole point of the shock is to, in fact, turn kinetic energy, the solar wind, into thermal energy and diverts the flow around the obstacle. Okay, so that's the role that is played by the shock. And when we look at these obstacles, and we're going to be talking mainly about the Earth and Jupiter, very well-behaved, sort of fairly simple obstacles, keep in mind there are also some extreme cases. Here we have Mercury, where sometimes the solar wind flow is so strong that it impinges on the actual object, and so you don't have a sphere of influence to protect, if you like, the planet. And then we have a situation at Mars where we have a very complicated, complex field, surface field, mostly in the southern hemisphere, so that standoff distance, that point where the solar wind is being stood off by the magnetic field of the planet, is very bumpy, and the topology of the interaction of those fields can be quite, you can have a changing topology as the solar wind goes past this very variable surface magnetic field. Yes? Yep. Oh, there'll be a shock up front. Yes. Okay, so I happen to have a couple of experts here in the room, so I can ask, do we have evidence that the solar wind magnetic sheath actually hits the surface, Catherine? It does. Yeah. Yeah. So it's extreme because it's not common, right? And yeah. Interesting point that it's more deflected than if you just took a statistical case. Someone else had that hand up. Yeah.
Theory is that if you push back the magnetic force, the
So I'm not going to talk about Mercury today, just because it's, you know, there's only so much we can talk about in one lecture. But it is a case where there is an interaction with the actual object rather than with an atmosphere of the object or a magnetic field of the object. And so we have to, this is sort of almost moon-like or Ganymede-like or Io-like in many ways. These interactions, less like a standard magnetosphere, more like an object sitting, a moon, more like a moon. Okay, we do have some people who work on the messenger mission to Mercury in the room, so maybe at the break there's some conversations. You have further questions, let's discuss it then. Okay, so I want to get on to some basic descriptions of the magnetosphere and the magnetospheric interaction with the magnetosheath and the solar wind, which goes behind the shock into the magnetosheath. And this standard sort of description of what's going on goes back to ChapmanFerraro in the 30s, where they were thinking if we had a magnetic field. So remember, the dipole field varies, oops, that's not supposed to have a squared there. I'm not sure why that squared is there, but I was going to write this up, that we can describe a dipole. B dipole is B0 R planet over R to the cubed, so that where we have we have a magnetic field like this. Here, this is B0 at the surface at the equator, and if we go out as a function of R, it drops off as the magnetic field strength drops off as 1 over R cubed. Okay. So then if we think about the situation where we have the solar wind coming in, it goes behind the shock, and then we have an interaction of the ram pressure of the solar wind, rho v squared, impacting the pressure of the internal field. And so the internal field will be b squared over 2 mu naught. And so we square this, we get our b0, 1 over r to the 6th. Now, when we say rho for the mass density of the solar wind, what are we really talking about? Mass density is what? Number density, right? Times what? Mass of the ion, right? Since that's the dominant. In the case of the solar wind, that's basically the mass of the proton. Okay, is it exactly the mass of the proton? What else do we have in the solar wind as well as protons? Electrons, but we don't worry about their mass, right? Not to 3 orders of magnitude. 3 significant figures we don't. What else do we have to worry about? Alpha particles, right? So I believe the average mass, we just say average mass, is 1.04 AMU, right? So this is what we talk about when we talk about mass density. And typical numbers for the solar wind, Earth, 10, right? It's like 10 is everything. I learned that this week. 10 particles per cubic centimeter. Okay. So it's roughly 10 AMU per cubic centimeter is the mass density. Okay, flowing along with the solar wind. Okay, but what about the currents at the magnetopause? We can just take the ram pressure and we can take the internal magnetic field, but we also would need to think about these currents here on the magnetopause. Remember, we talked about that curl of the magnetic field on the magnetopause boundary. You know, you could sort of like double the magnetic field if you like, or you might say we slow down the solar wind so we decrease the amount of the effect of the ram pressure on the other side. In either case, I'll come back to this issue in a minute, you can solve for the distance at which these pressures are equal, and so you end up with this expression for the distance to the magnetopause in terms of the planetary radius that varies as the 6th root of b squared divided by 2 mu naught rho solar wind, v solar wind squared. Okay, with some number in front, which is not too desperately far from 1. Okay, so I'm being sloppy here. There is a detailed way in which you can discuss this interaction with the magnetopores. You can look at the history side, which is very well described in previous lectures. Last year's lectures really cover this very well. There's also the lecture from a couple of years ago by Toffletto, which covers this very nicely. I'm keen to get on with the magnetospheres and not get obsessed with the magnetopores. Yeah? Sure. No error here. No squared. I should have let you point that out to me. You could have been smarty pants. I'm going to make lots of mistakes of factors of 2. Okay. You ready? You're going to get these notes, by the way. I apologize I didn't get them to you in advance. Okay. So we have a magnetosphere. We have this rough balance of solar wind ram pressure and magnetic pressure. And so we end up with this, what we call Chapman-Ferraro distance, where we have this approximate 1.2. And, you know, if we're going to be astrophysicists, you know, well, let's just say it's basically 1. B squared, rho solar wind, B solar wind. Okay, so let's look at this. How does rho vary with distance from the sun? This is a reminder from yesterday. Not yesterday, Saturday. How does the solar wind vary with distance? And so how does this component vary with distance? So discuss amongst with your mates and come up with answers to these 3 reminder questions based on what was discussed before. Yeah.
So the expression is like the whole inverse of the
This is rho v squared is ram. Oh, you mean this thing here? Right, right. It's 1 over the ram pressure to the 6th. Yeah, right. Yeah. Yeah, this is a bracket in there. Yeah, good point. When am I supposed to, what's the timing, by the way? Okay. Oh, this red dot? Oh, okay. You know what's it works well here. You put it up there and it gets, oh, okay. Okay, where are we? Density. How does density vary with distance in the solar wind? 1 over r squared. Okay, you're just spreading it out with distance. How about v solar wind? Roughly, almost constant, right? Okay, so how does 1 over rho solar wind v squared all to 1/6 power vary with distance? Get bigger or less with distance? Goes up? How much? Distance to the 1/3. Yeah, okay, so this means then that we would increase our magnetosphere. So this means you take the Earth's magnetosphere and you move it out through the solar system, it will get bigger, right? Because the ram pressure gets less. Okay. So this sort of makes sense then when we put in these values for the planets, then these are the sort of distances that you get. Now look at these fields. These are the values of the fields, B0 at the equator. And I put them in Gauss. Not that I particularly prefer Gauss, just that it's a number that's close to 1. You can see here. Now, Mercury, it really also shows how piddly, I hate to say this, it's kind of piddly little magnetic field of Mercury, and just how big and beefy Jupiter is, okay. But also what's remarkable is actually that these are all pretty similar, right? Apart from Jupiter and Mercury, they're all pretty darn close. Kind of interesting, interesting. Very different sized objects, very different kinds of objects, and yet their surface fields are more or less the same. And actually, apart from a few strong regions, the average surface field of the Sun is probably about a Gauss, wouldn't you say? Carl's nodding his head. Interesting. Coincidence, maybe. Yes, coincidence? She says it's a coincidence. Good. Not a cosmic convergence of some kind. We are in Boulder after all. Right, okay. Okay, so when you put these together with these variations in solar wind with distance, the calculated standoff distance, the Chapman-Ferraro distance, you can see is much larger for the outer planets than from the inner planets. But the other thing is interesting. This is the calculated value, right? And this is the observed value. And you can see, let's go through these. Works pretty good for Mercury. Not too bad for the Earth. Not so bad for Uranus and Neptune. Total failure for Jupiter. The actual values. And I've got two values there because it turns out that the magnetosphere distance has a bimodal distribution for Jupiter and Saturn. Perhaps related to the bimodal nature of the solar wind out at these giant planets. But you'll see that in the case particularly of Jupiter and to a certain extent of Saturn, they're much bigger than you would predict from simple Chapman-Ferraro theory. Okay, so what's going on here? Well, when you look at where this vertical line shows where the dipole would be, magnetospheres would be for a dipole, and you see Jupiter is about twice as big as predicted that way, and the answer is you have to have some pressure, some additional pressure inside that's pushing out, resisting the solar wind ram pressure, and the case of Jupiter and Saturn, this is pressure associated with large population of hot plasma that's inside. Okay, and we'll talk a lot about that in a few minutes. So what is a consequence of this when we think about just this standoff distance? Now for the Earth and a dipole, we just talked about how you get this variation with ram pressure to the minus 1/6 power. And so here's the Earth. And for Jupiter, we have a variation that's not 1/6, it's 1/3. Now a consequence of this is that if you increase the solar wind ram pressure by a factor of 10, for the Earth, you only change the size of the magnetosphere to 0.7 of what it would have been with a more normal ram pressure. Whereas at Jupiter, it's much more squishy, much more compressible, and you halve the size of the magnetosphere. So by putting the hot plasma inside, which does not have this strong variation with radial distance, when you calculate the ram pressure, you end up with a much squishier, more variable magnetosphere. Okay, so let's think about this. Here we are, we have our magnetosphere of Jupiter, large standoff distance, somewhere between 60 and 100 Jovian radii. Remember that Jupiter is 10 times the size of the Earth. Okay, so we're really talking a large volume here, and we have a lot of plasma inside. When we look at this quantity beta, the plasma beta, NKT over B squared over 2 mu naught, so this is the ratio of the energy, the pressure, it's related to energy density, but it's the pressure of the thermal plasma inside this magnetosphere to the pressure of the solar wind, the pressure of the magnetic field, then you end up with a value which in regions, okay, so if we go to a empty part of the magnetosphere, is beta going to be high or low? You go to a region where there's very little plasma or very cold plasma, is beta high or low? It's going to be low. Give me an example of a very low beta plasma in the heliosphere? Solar corona. Excellent. Very strong field. Still a lot of hot plasma, but there's a heck of a lot more magnetic field there, right? Okay. Another place where we have a very low beta is actually in the lobe regions outside of the sort of high latitude regions. Whereas in the current sheet or plasma sheet, beta can be very high. In the case of Jupiter, we have regions where the thermal pressure of the plasma is 100 times greater than the magnetic field. So who's going to push who around, right? You can see that if you're in a region of low beta, it's the magnetic field that totally dominates and tells the plasma where to go. Other way around, when you have a high beta, it's the plasma that's pushing the field around. Okay, so here we have what we end up for our balance. We have to add in not just the round pressure balancing the magnetic field of the planet, but we have to add in the NKT that's resisting it from the thermal plasma that's inside. And where is this thermal plasma? Well, it starts off coming from Io, the volcanic moon of Jupiter. That's where the plasma comes from. But it spreads out and fills this vast region that is 60 to 100 times the size of the planet. Okay, so where does this hot plasma come from? Well, in the case of Jupiter and Saturn, it's both cases, it's moons. And in the case of Jupiter, it's heavily Io, this volcanic moon covered in volcanic eruptions, producing sulfur dioxide gases that are spewed out. We can see them in terms of neutrals that are stripped off from the atmosphere. We also have a very charged plasma that's in here. In the case of Saturn, there's the moon Enceladus that has plumes which are spewing out water into the magnetosphere. So these moons are heavily embedded in the magnetosphere, and to compare the different planets, Mercury, Venus, Earth, and Mars have weak or no magnetic fields, and the influence of the Earth's magnetosphere really barely extends out to the moon, only on the tail side. So a very small fraction of its orbit does the moon spend in the magnetosphere. It's like 5%, I think. Maybe that was a homework problem. So if you look at the giant planets, and notice this is a log scale, you'll see that the main moons, Io, Europa, Ganymede, and Callisto, the Galilean moons, are deeply embedded in the magnetic field of Jupiter. And for Saturn, we have Enceladus, which, although it's small, has these plumes producing material, and Titan is there on the periphery. Okay, we'll skip the other ones for now. Okay, so we need to talk about the dynamics of the magnetosphere. And I know that Terry started talking about this in terms of reconnection, and that Mark talked about this in terms of magnetospheric structure. And what we have driving the magnetosphere is this reconnection process, whereby magnetic field of the sun connects with the magnetic field of the planet on the day side, opens up, carries over the top, and is closed on the night side. And so, yes, I have to do the Dungy dance, where you have a magnetic field that opens up, is carried back across the polar cap, reconnects on the night side, and comes back. And so we have a flow of flux through this magnetosphere that is being driven by the solar wind. Now, this all looks very nice, and the way I'm doing this suggests that it's a sort of steady process. Whereas in fact, it's a much messier process, very variable. The opening rates can vary depending on the conditions in the solar wind, and the closing rates will depend on how much flux is built up. And of course, this is a much messier way. There's a build-up of flux in the tail, and then you get a big storm, substorm. And so they're variable rates, but of course, they've got to average over time. Otherwise, the Earth's going to be losing flux. It's going to have more and more opening. You've got to close it at some point, right? So in a steady state, you've got to remember that these pictures, again, a 2D picture of a very complicated 3D structure, but you have to remember that they must be equal over time. Now, notice when we look down that there is this return flow in the equatorial region. So we're opening up this flux, we're carrying it down to the tail, reconnecting it, and bringing this flux back, and then opening it up again, right? And that return flow is key in order to keep the flux conserved. Yes? Is a possibility of what?
Flux injection from the first
Injection. You mean the flux from the solar wind adding? Leaking in, you mean adding to the... I'm having a hard time seeing how you could add flux from the solar wind to the magnetosphere on the front side. Can you think of a way of doing this?
Well, there might be some small amount because you could imagine having X lines up in the cusp region,
Right.
from a northward magnetic field, so it's not going to be like this. And you do get some minor reconnection going on in there, and that implies at least a little bit of addition. But it wouldn't be a lot. It's a good question to ask how much it would be.
Yeah, yeah.
Not entirely impossible that some small amount of flux could be added, probably up in the low region associated with the exploits of the cusp region.
But you're going to have to remove it later, right? You can't keep adding. You can't be adding it constantly to the planet. Okay. Okay. So then, of course, we'll be talking about the rotating part in a minute when we talk about Jupiter. So I'm going to describe what's driving this Dungy flow in terms of a paradigm that all the textbooks that I know of use, which is to describe things in terms of electric fields and currents. This is called the EJ approach, and every textbook I know uses this. But there's a new fashion, and when I say new, it goes back to Parker 1996, which isn't particularly new, and Vitenis Vassiliounis in the textbooks that you have here and other places has been talking about taking this BV approach. Now, I have yet to find a textbook that uses the BV approach. And so I'm going to talk through the EJ approach. But I'm hoping that next summer school we will have a nice description in the BV approach. And I see Carl putting his hand up, and he's probably saying, oh, well, Vitenis Vassiliounis has it in his textbook. Ah, that's interesting. Yes, okay, touche, good point. But I think if you look at all of the readable textbooks, and I don't mean that, I do not mean that as an offense, and I don't mean an offense to the astrophysicists, but if you look at the space physics textbooks, and I've looked at all of them, none of them take the BV, they all take the EJ, okay? So I'm doing this, but I recognize that there is a better way of doing it. Okay, so we have this Dungy cycle, just as I danced out, and so, yes? Okay, sure. Okay, BV is magnetic field and velocity, plasma flow and magnetic field. And you can describe all of plasma physics, pretty much all, but not all, but most of plasma physics in terms of the flow of the plasma and the magnetic field that's frozen to it, okay, basically. The other way is to talk about electric fields and currents. And it's convenient that way to do so, but in fact, they're both very hard to measure and directly. And one could argue that really you should be talking about the stresses and the flows, responses, conservation of mass and momentum associated with interactions between the magnetic field and the flowing plasma rather than currents and electric fields. Okay. Somewhat of a philosophical issue, but that's what it stands for. Okay. So we can talk about an electric field, which is this green arrow here that goes across from the dawn to the dusk side. We're looking down on the magnetosphere here, and you can describe a convection that's driven by the solar wind that harnesses the solar wind kinetic energy and turns it into stored magnetic energy. And we will assume some kind of efficiency of reconnection that's between 10 to 20%. That is, that 10 to 20% of this, of the potential energy that's available in the solar wind gets harnessed by the magnetosphere. So if you look at where this comes from, you can do your E equals minus V cross B, and you can see that you end up then looking sideways here, that you have a B coming down, V going this way, you'll end up with a E going this way. Okay, so that's looking down, it's this E across the tail. So here you can say that, and this is a crude approximation that is used, as I said, often in pretty much all textbooks that you can find, that you have a constant east-west, a constant dawn-dusk electric field across the magnetosphere that comes from reconnecting the this reconnection process on the day side, driving this flow. So then you can look in the tail and say, well, if we have this dawn-dusk electric field and we have a B, which is now in the equator, coming out of the board, then you end up with a V that is this return flow that happens in the equator. Okay? So then you can then say, well, what is this V convection that comes from the solar wind? You can then plug this in and say, given a dipole magnetic field, then this convective flow, notice that it increases with distance from the planet, so it's stronger near the magnetopause, weaker nearer the planet. That varies with the solar wind strength and the reconnection efficiency. Okay. So this is an approximation that helps describe how you drive this magnetospheric flow inside the magnetosphere, and then when you map that flow onto the ionosphere, then you end up with these cells, two cells, where you have in the open region, the region of open flux, you have from the sun away towards the tail flows on the inside, and then a return flow on those field lines that map back to the equator, okay, equatorial region. So you end up with these cells in the ionosphere. Okay. And when you look at the aurora, then you find that the auroral region is pretty much maps out this open-closed boundary. So you can imagine there are a lot of currents associated with this interaction that flow along the field, delivering electrons that excite the gases of the atmosphere. And Marina will be talking a bit more about that, I hope, later today. Okay, so I've done the simple dance, I've shown you the simple diagrams, I've made this approximation of using the electric field driven by a level of efficiency of this reconnection process. But of course, in reality, the situation is messy, and it's 3D, and those movies those simulations that you have been looking at in your labs try to capture a lot of that complexity associated with a variable upstream solar wind, a variable direction of the interplanetary magnetic field, a build-up of flux in the tail, and so on, trying to capture the 3D complexity. And of course, the dynamics is a major part of the space weather that infects the Earth. We're interested, as people living on the Earth, how this change in the magnetosphere, this dynamics affects us. And so not only does it pay a lot of salaries of people whose job it is to predict space weather, but it affects a lot of technology, as we'll hear about later in the week. So we have a dayside magnetopause, which responds to the direction of the solar wind, responds to the ram pressure, and we have tail reconnection, ejecting plasmoids, but also leading to movement. Once you eject a plasmoid, you'll see these field lines snap back towards the planet. And as they snap back towards the planet, they bring energetic particles in towards the Earth. And this whole business of predicting these and understanding them is this business of space weather. So I'm going to take a break right now, because we're now going to start talking about rotation and how the effect of coupling to the actual planet and the planet's rotation is important. So let's take a break.